Introduction to Organic Chemistry Part 2. Ionic and covalent bonds. Ionic bonds attraction of two elements having opposite changes results in the formation of an ionic compound. Ionic compound occurs when a metallic element reacts with a non-metallic element, due to metals usually having excess valence electrons that are needed by non-metals. Types of ionic compounds. Binary compounds composed of only two elements. Example: sodium chloride, water. Ternary compounds composed of three or more elements. Example: sulfuric acid, chalk. Ions monatomic atoms of different elements that either gained or lost electrons. Charges can be determined using the periodic table. Polyatomic tightly bound groups of atoms that behave as a unit and carry a charge. Cations atoms that lose an electron gaining a positive charge. Anions atoms that gain an electron gaining a negative charge. Covalent bonds. Bond formed between two non-metals that share electrons. Non-metallic elements tend to accept electrons from a metallic element to be stable. Non-metallic elements can also react with each other to become stable, usually illustrated using the Lewis structure configuration. There are several different ways we can draw organic compounds. One way to represent organic molecules is through Lewis structure. It illustrates what atoms are connected and they show bonds and in lone pairs of electrons and molecules. Lewis structures, electron dot structures, represent the valence electrons as dots around the chemical symbol of an element. The electrons are distributed in circular motion, one at a time, with the next set of electrons written as a pair of the first set. Lewis structures may also be written for ions, although these are rarely used. An atom is already stable if it already has 8 valence electrons around it, with two sets of electrons on each side. Types of covalent bonds. Covalent bonds can be classified based on the number of shared electrons and the polarity of bond formed between two atoms. Based on the number of shared electrons, a covalent bond may be classified as a single, double, or a triple covalent bond. Based on the polarity of bond formed, the covalent bond between two atoms can be polar or nonpolar. Types of covalent bonds based on number. Single covalent bond, one pair of electrons is shared, denoted by a short line. Double covalent bond, two pairs of electrons are shared, denoted by two short line. Triple covalent bond, 3 electrons are shared, denoted by 3 short line. Types of covalent bonds based on electronegativity. Electronegativity, measure of the ability of an atom to pull the bonding electrons toward itself, increases in the periodic table as you go from left to right. With the exception of noble gases, elements on the right of the periodic table are more electronegative than those on the left. Noble gases do not have electronegativity values because they are already stable. Polar covalent bond occurs between two atoms having unequal electronegativity. Nonpolar covalent bond occurs when there is an equal sharing of electrons. Acids and base. Bronsted and Lowry definition. Any species that has hydrogen can potentially act as an acid. Any species that has lone pair can potentially act as a base. Acid is a proton donor and base is a proton acceptor. Acid-base reaction. Proton transfer reaction. Both an acid and a base must be present in an acid-base reaction, because an acid cannot lose a proton unless a base is present to accept it. Most acid-base reactions are reversible. Conjugate base is the resulting species without the proton when an acid loses a proton. Conjugate acid is the resulting species with the proton when a base gains a proton. Acidity, measure of the tendency of a compound to lose a proton. Basicity, measure of a compound's affinity for a proton. The stronger the acid, the weaker its conjugate base. A strong acid is one that has a strong tendency to lose a proton. This means that its conjugate base must be weak because it has a little affinity for the proton. A weak acid has little tendency to lose its proton, indicating that its conjugate base is strong because it has a high affinity for the proton. Thank you for watching. Please subscribe and stay tuned for part 3.